Welcome to 1010 Analytics. In this video, we'll be talking about what is overfitting in machine learning, why overfitting can be bad, and we'll go over 6 practical approaches for dealing with overfitting and high variance. And we'll also go over some algorithm-specific approaches for dealing with overfitting. So what is overfitting in machine learning? Overfitting happens when a model learns the training data too well, and it ends up capturing noise and random fluctuations in training data and learns them as concepts. And this usually can be detected if the model does much better on the training set as compared to the testing set or the validation set. So for example, a model shows 99% accuracy on the training set and about 55% accuracy on the testing set. So you can see it's overfit to the training set. So in the image below, you can see overfitting where the model has captured all the single points in its predictions in the training set. So this shows high variance, and you can see that most of the noise and random fluctuations have been captured here. And the other way around for this is underfitting, where none of the points have been captured almost, and no pattern has been captured at all. So it's the other extreme. And a good balance usually is low bias, low variance, where you've managed to capture the underlying pattern and have not captured the noise and random fluctuations. Now, why overfitting can be bad? So this can negatively impact performance of model on unseen data because it will just not be able to generalize well. So for example, a child is trying to learn what a tree looks like, and only oak trees are in the images of the training set. So it will be overfit if the child concludes that a tree is a tree only if it has the similar height, width, leaf pattern, branch pattern, and all the other distinguishing features of oak trees. So essentially, if you give it a pine tree or a maple tree or willow tree to classify, it'll just say that that is not a tree at all because it does not have the exact same leaf pattern and branch pattern as an oak tree. And the other extreme is underfit, where the child just concludes that anything that is green is a tree, which is too simple. And a good fit could be anything that has leaves, branches, or a trunk can be considered a tree, which may not be perfect, but it does a good job. Now let's look at some practical approaches for dealing with overfitting. So first on the list is dimensionality reduction. So if you reduce the dimensionality of the feature space by obtaining a set of principal features, you may be able to deal with overfitting. So one way to do this is through feature extraction, where you'd create new features by projecting your existing data to a space of fewer dimensions. So a couple of ways for doing this is through principal component analysis, or PCA, and linear discriminant analysis, or LDA. So both these methods, they perform linear mapping of your existing data to a lower dimensional space. And next we've got feature selection, where you can just select a subset of original features by removing redundant or irrelevant features. And this can be automated as well. You don't have to do it manually, by combining evaluation metrics with algorithms. So you could use wrapper methods, filter methods, and embedded methods. And I'll not be going over exactly what these are because it is kind of out of scope for this video. Now let's look at another way to deal with overfitting is by getting more training data. So a good example for this is, let's assume if a training set comprises of me and all my friends, and an algorithm might associate my name, Mohit, with has a beard, because I have 3 other friends named Mohit and all of them have beards, and I do consider this to be a beard. And if the training set was increased to the entire country of India, There could be thousands of people named Mohit. Maybe only 50% of them would have beards. So in this case, getting more training data will prevent algorithms from making a faulty assumption that anyone with the name Mohit has a beard. Now, another way to reduce or deal with overfitting is by reducing noise in training data. The noise is just any unwanted data that does not help explain the feature itself or the relationship between the feature and the target. And outliers can be considered noise in some cases. So this can be detected visually by plotting box plots or scatter plots, or mathematically through descriptive statistics. And once you find outliers, don't just blindly remove them. You need to look deeper into understanding why they exist. And if the outlier provides no value, then just remove it or replace it through imputation. And another interesting way to reduce noise is through unsupervised methods. So this is basically anomaly detection using unsupervised learning. So by unsupervised learning, you could use density-based methods, clustering-based methods, or support vector machine-based methods, and even autoencoder-based methods for doing this. So essentially, you're looking at your training set or whatever data you have. You're trying to run it through an unsupervised learning algorithm to find outliers or anomalies in the data that could be considered as noise. And don't just blindly remove them again. Look into it, understand why it exists, and then if it provides no value, only then remove it or replace it through imputation. And another way is through bootstrap aggregating or bagging for dealing with overfitting. So bootstrapping is a sampling technique. You choose a set number of samples with replacement to create new training sets in parallel. You're generating more data almost. And then you run the algorithm on each of these samples, and then you aggregate them using, so the predictions from all these algorithms run on these training sets are aggregated to make a final combined prediction. So for aggregation, if you're using a classification type problem, then you could do majority voting to decide what to classify. If you're using regression, you could just take the average from everything. And one advantage of this is that this improves the stability of algorithms, in the end just reducing variance. And the disadvantage is that it's computationally expensive because you're running so many different training sets in parallel. Now, another way to deal with overfitting is through regularization. So this is usually used in regression, in neural networks, and deep learning. And essentially, this helps us choose preferred model complexity. Now, by model complexity, I mean the degree of the polynomial. If you're thinking of it in terms of regression, it would be that, let's say, a polynomial with degree 2 will have x squared or x raised to 2 as the most complex term, and polynomial with degree 8 will have x to the power 8 as the most complex term. And the magnitude of this coefficient increases exponentially with increase in complexity of the model, as long as the coefficient is greater than 1. It should not be between 0 and 1. And what regularization does is we're trying to add a constraint to how big the magnitude of this coefficient can get. So this is done by adding a penalty term lambda to the objective function of algorithms. So this penalty term has a constant lambda actually that can be set either manually by us or through hyperparameter tuning. And some common types of regularization are L2 regularization, which is used in ridge regression, where you're using the penalty term equivalent to the square of the coefficient. And L1 regularization is used in lasso regression, where you just use the magnitude or the absolute value of the coefficient as the penalty term. And you also got elastic net regularization, where you just combine both L1 and L2 together. And I would love to go deeper into regularization, but it is out of scope for this video. And another way for dealing, or rather not dealing, but kind of trying to prevent overfitting, is through cross-validation. So one type of cross-validation is called k-fold cross-validation, where you divide your training data into k number of subsets. So let's say if we take k equals 5, we divide our training data into 5 different subsets, and then we'd use 4 of them as our training data and 1 of them as our test data. And this is repeated until each subset acts as a test set at least once. So we just have to repeat it 5 different times because our k equals 5. And in the end, we can just average the error estimation over all k trials to get an evaluation score. And another way to do cross-validation is through leave p out cross-validation. So you'd leave p number of data points out of the training data. So for example, if p, you can select p as 20 from an overall training set of 1,000. So you'd have 20 for testing and 980 for training. And however, the remaining number of, this has to be repeated until all combinations are used. So every single way you can create 20 different points as test sets will have to be used, which would be very computationally expensive. So normally what people do is they use leave 1 out cross-validation, where you select p as 1. So you just have 1 data point as your test set. So if you've got 1,000 points, you'd have to repeat it 1,000 times. And now let's go over algorithm-specific ways to deal with overfitting. So if you're building linear models, you could apply regularization, as we discussed earlier. And also same can be done for artificial neural nets. You could apply regularization. And another thing you could do is you can decrease the number of hidden units you've got in your neural net. And if you're doing k nearest neighbors, you could increase the value of k. So let's say if you're using a value of k as 1 or 2, you might end up capturing noise as you're looking at the nearest 1 or 2 neighbors. So if you increase the scope of the neighbors, then you might end up generalizing it better. And if you are making decision trees, then you could prune the decision tree, as in you could reduce the size of the decision tree by removing sections of the tree that provide less value. And that is it for this video. So if you found this video helpful, consider subscribing to this channel in case I upload something interesting that catches your eye. Thank you very much for watching.